All right, yeah, so I'm Evan Owen. I'm the Director of Engineering at CoTap. And my talk tonight is on Groupcache and how we used it to make media messaging fast. And I think I just bumped the HDMI. There we go. Okay, so CoTap. Just a quick intro so that my talk makes sense. This is kind of our X for Y. We're WhatsApp for work. We're a messaging app. We help you communicate with your coworkers. And we have functionality that makes it easier to work. So we have a company directory. You don't have to swap phone numbers. We have support for multiple devices, sync your data. We have native applications. And then we have integrations like Salesforce. And we also allow you to send files, photos, and video. And it's those last three that we wanted to do really well. We wanted it to be fast. We wanted it to feel very natural, and it's pretty hard. Just to give you a bit of background, I actually come from Ruby development. I think actually I've noticed a lot of Go developers come from a Ruby background for some odd reason. And we're a Ruby shop primarily, but I had been investigating Go, becoming more and more interested in it around a year and a half ago. And when we ran into this problem of wanting to send media very quickly and efficiently, I started seeing that Go might be a good way to solve this problem. So again, the challenge was how can we deliver user media to hundreds of recipients very quickly and make it feel fast? And so we have the ability to create groups of up to 1,000 members right now. And when you send a photo, you want that message to be delivered very quickly, and we want the photo to show up in the right size across maybe a poor mobile network and have it just feel as fast as possible. So our goals, basically sending should feel as fast as transmitting the data. We don't want to wait for some sort of resizing operation to happen when the user is sending the photo. Obviously we can't help you if you have a poor network. And the clients are resizing the images to some extent, but we want to feel as fast as just sending the data to the server, sort of fire and forget. Finally, we wanted the latency between sending and receiving the message to be as low as sending a text. So when it says sent on your phone and the other user maybe in the same room as you sees the message on their phone, it should be as quick as sending a text message. There shouldn't be a long 5 or 10 second delay just because we're waiting to resize this image. Finally, delivery time should remain constant as the number of recipients grows. So if you have a large group, we don't want that message to take a lot longer to get delivered. And I'm sure you're kind of starting to think about the challenges involved in getting this done. Finally, we want to allow one-to-many delivery with dozens of resolutions. So you might have a phone or a tablet, or you might be on the web with a browser window or on a desktop app. And we have all of these apps, and we want that image to be optimized for your device so that you can download it quickly, but we don't want to wait forever for this to happen. So in the past, I've seen a lot of patterns for image processing, and we kind of thought through these. So the easiest one is to just resize the image or video when it gets uploaded, right? So as the user is uploading it, you kind of block, you do the resizing operation, maybe you store it in S3, the different sizes you support. It's pretty easy to implement, but it makes the sender wait. It feels awful, especially if you're on a mobile network. So we ruled that one out right away. Another pretty common pattern is what I call asynchronous on upload. So you just take the data and then maybe you kick off an asynchronous worker and you resize it in the background. That's a little harder to do, but it makes the experience feel better. A surprising drawback for messaging is that you have to wait until the image is processed before you can actually send the message, or else the recipient doesn't get anything and the client has to retry over and over again until the image is actually available. So it makes the client logic a lot harder. And this didn't seem like a great option for us either, even though this is a pretty common option, especially in the Ruby world. There's like a couple gems that make this pretty easy. It just doesn't work for messaging very well. So what we landed on was we got to do this on demand. We need to resize these images as soon as the user requests them, and ideally they should be ready as soon as they want them. So I think there's a few open source tools to do this. I think there's one in Python that's pretty well maintained. You can just kind of set up the server, give it a source directory of images, and ask for an image of a certain size, and it'll resize it for you and give it to you. I think it uses ImageMagick or Graphics Magic under the hood. It's a little slow, a little complex, and didn't do everything we need, but that's one way to do it. Also, if you have 1,000 clients asking for the same image, it's resizing it 1,000 times. And so you're wasting a lot of processing power. So we realized we needed to do these things, and I had stumbled upon Groupcache around this time that I was researching Go, and I just immediately realized that this could help solve our problems. So Groupcache is actually a library open source by Google, written by Brad Fitzpatrick. He actually worked at LiveJournal, developed Memcache, also worked on OpenID, and it was originally written for dl.google.com, and I did a little searching, realized he actually gave a talk on this here at GoSF in September of 2013. So if any of you are here, this will be very familiar, but I doubt that it's familiar to everybody. So this is slides from one of the talks. I'm not sure if it's the talk he gave here, but there's a lot more info there. So again, Memcache alternative. An interesting difference is Groupcache is read-through only, so you can't set any values. You ask for a value, and if there's a miss, you can provide it with a value to fulfill that miss, but you can't set or expire anything. So that changes how you might use it. It's a Go package, acts as both a server and a client to peers, so it's distributed like Memcache, and it requests items from its peers. And because it's distributed and because it uses a consistent hash ring, there are coordinated cache fills. So if you have a lot of clients asking for the same key, even if they're hitting different peers, you actually don't run into the thundering herd problem. Your cache fill only happens once. So this solves the problem I mentioned earlier. And finally, it actually handles replication of hotkeys across the cluster. So if you have one key that's requested more than others, and you have clients that are hitting all of the peers in your cluster, those will actually be cached locally. There's a little bit of probability going on, and I think there's some optimizations that are still to be made there, but it helps. So kind of a visualization for that. If you have a cluster of Groupcache nodes, you have a request coming into node 2. The consistent hash ring says that item is on node 5. It'll go to node 5 and fill that cache request if it's not in the cache already, and then return the item to the user. Again, if you have concurrent requests for a given key, they all go to node 5. And the way that Groupcache is set up, if all of those requests hit node 5, all of those requests simply block and wait for that cache fill to happen, and the data is simply returned to all the clients when it's ready. So if your image resize takes half a second, one client requests it, another client requests it 250 milliseconds later, then the rest of the clients only have to wait half a second because it was already being processed. And then again, finally, if these clients on the edges here also get a lot of requests for that item, they cache it in their hot cache. So an interesting thing, because these are in-memory caches and they're immutable, you kind of have a few restrictions on what you can cache. The main and the hot caches are LRU caches, so least recently used, and you just set a size. I want a maximum of, maybe 512 or 1024 megabytes, and Groupcache just evicts items that haven't been accessed in a while as you reach that limit. Data is cached and transmitted using protocol buffers. So you can simply define your structs, whatever data you want to store, it will marshal and unmarshal into those protocol buffers and store it in memory. And there's no set or expire, once again, like I mentioned. Once it's filled, data is immutable. So Groupcache is ideal for data that doesn't change a lot. Or alternatively, you can adjust your keys to represent the change in the data and simply let the old objects fall out of the LRU cache. And if the remote node can't be reached, the key is just filled locally. So if for some reason there's a network partition or a node goes down, you can still fill that cache request on whatever node the request comes in on. So here's an example, just a couple code examples. You can set up the pool just by passing in the node addresses for your own local node and the others, so you have a consistent set of peers to calculate your consistent hash ring off of. And then here's where the magic happens. So you define what's called a getter function. There's an arbitrary context struct that you can pass in. We haven't actually used that so far, but I imagine you can pass some sort of other variables that affect how your cache value gets generated. And then obviously the key that is being requested. And then a sync, which is an interface that allows you to pass back whatever data you're generating to the requester. So obviously, we're not handling errors here very well, so forgive the code. But in a simple way, you simply do your operation. Maybe it's a fetch request to some external resource. Maybe you're doing some generation that takes some time. In our case, we're resizing images and processing video, et cetera. And then you simply set the bytes directly on the destination sink. And you pass that getter function to a new cache group. And the cache group defines the maximum size of the LRU cache, and you give it a name. And for a cluster of group cache nodes, that name needs to be unique for the getter function that you're passing. So whenever you request an object from this group, it will execute this function on one of your nodes. It might be the local node, it might be a peer, it might already be in cache, but this function will be executed only once in your cluster, and then cached once it's fulfilled. So that's kind of an example of how you might request data. And here, simply passing a pointer to a byte slice, it allocates, passes you back the data, and then you can do something with it. Maybe, most likely you're going to serve it to clients requesting that data. And again, it'll be filled from either local memory, if it's like in hot cache, or maybe your current node is the primary for that key, or it might get it from a peer cache or computed either locally or on a peer. So here's how we use Groupcache for media. We actually decided to use content addressable storage, so we just calculate the hash of the data that we're storing. That way it's easy to make sure that we have unique keys for all of the originals, and we don't need to store the original name, so this also keeps it a little bit obscure. So we keep those in cold storage and just have the hash of the content as the key. Then we have a small group cache group in front of those originals, so that if you have multiple clients with different resolutions, that original is in memory, and we can resize for those multiple resolutions very quickly. We don't have to go back to the cold storage. And we actually are resizing the images in process using OpenCV bindings that we wrote. We looked at a lot of options for the resizing, and turns out image magic and graphics magic are pretty slow, and we didn't want to shell out. So we're doing all of that resizing in process, and it turned out to work very well. I could actually probably do a presentation just on that. That was pretty fun. And then we actually have a larger group cache in front of those resized images to allow the final image product to basically stay in cache longer. So we have a larger LRU there. And then, so one of the reasons we're doing that is because we found that a lot of clients have the same size. So we have a lot of iPhones and a lot of desktop apps that have the same size requirements. And so allowing those clients to take advantage of the resized versions ended up being very helpful. So we actually have 2 layers of group cache. And then finally, you could just obviously put a CDN in front of that outermost group cache and get your images closer to your users, those edge locations in, say, Asia or Europe. And potentially, if you wanted to do your own CDN, you could put group cache clusters in data centers and simply allow them to be sort of regional caches for your primary group cache cluster. I think that would work pretty well, but we actually haven't finalized the implementation of a CDN, but I would just use a standard CDN for that, and just use Groupcache as your custom origin. So it looks something like this. We have a URL that has the hash of the content and the size that you're requesting. A request comes in, it gets the original, and it might be in the original cache, and then we have another layer of group cache instances that are actually doing the resizing through OpenCV there. And so worst case scenario, it has to go all the way back to the original, but most likely there's something in one of these two caches. Either it's the resized one that the client's wanting, and then it's we've seen basically 0 millisecond. I think we need to increase the resolution of those metrics because I have no idea how fast it is. It's below 1 millisecond. And then otherwise it's having to do the resize, which is ending up to be pretty quick, in the order of a few hundred milliseconds for most images. So that's it. What we do is basically when we send, it's just an upload. We immediately kick off a warm operation, so we request the commonly used image sizes immediately. And the client then can send the message without waiting, and we can guarantee that any recipients will be able to retrieve the image in the size they need. They might have to wait a little bit, but for the most part, the resize will already be complete when they go to get it. So best case is it's just network latency. Worst case is it's not in the cache and there's a single processing operation to warm that cache. So here's kind of a simple example of what one of these protobuf structs looks like. It uses struct tags to define the protobuf properties with the type and the name. And if you modify this, actually, you should just use the proto file and generate the code. We ended up doing it ourselves because we wanted a little bit more control over it, and we don't have any other languages we're using protocol buffers with, but you should probably just use the proto file. And then here's an interesting thing. We actually added a method to generate HTTP headers. So we're storing the content type and the last modified date in the protocol buffer struct, and then we can simply generate the image headers dynamically like that. And then when you go to serve it up, you just loop over those headers, set your response header, and then you can very easily set your mod time and the read seeker for HTTP ServeContent, and the rest is magically handled by the standard library. In fact, I wasn't aware that ServeContent handled byte ranges, but we discovered when looking at the logs that it does. There were some clients that were requesting byte ranges, and ServeContent was just pulling the image out of the cache, giving the byte range back to the client that it was asking for, and it just worked magically. So this ended up being a great pattern. Finally, this is really great, so everybody should instrument their services. There's great stats that Groupcache gives you. You can get the group stats and then the cache stats. We combined them and created an endpoint with a bunch of JSON that we could analyze and measure. So we just expose that locally. We monitor that with Sensu and send those to Graphite, and then we can kind of see how our caches are doing, what the performance is like, if we have a good hit-miss ratio, that type of thing. And then a few gotchas. So we ran into a few interesting problems. One of them early on was inconsistent hash rings. So Groupcache, it's not a strictly distributed hash table, so it doesn't actually keep track of your hash table on its own. You kind of have to make sure that the peer list is consistent across your cluster. So always make sure that the local node is included in the peer list, and you have to update those peer lists as quickly as possible. So if a node goes down, make sure that all the other nodes know about it, or else you'll start needing to generate more, basically more of those requests will hit bad nodes, and it'll start trying to generate those locally, and you'll have increased CPU usage across the cluster. One idea would be to use something like console or surf, if anybody's familiar with the HashiCorp console. That way you can get very, very quick feedback of nodes that are going down and update those peer lists. You can do that without reloading the program. You just set peer lists on the group, and it'll immediately update the hash ring. Finally is a getter function inconsistency. So when you fill one of those cache misses, you have to make sure that it doesn't matter which node that function is called on. If for some reason there's a difference between running that function on node 1 or node 2, it's indeterminate what your client's going to get. So that function should be, you can't depend on a local file being present, for instance. You need to make sure that that function can be run anywhere across your cluster. Also, cache memory usage. Make sure you leave enough headroom. Currently, Groupcache actually copies the bytes out of the local cache in order to return it to the client. So you need at least double the cache that you have locally in order to handle any potential requests that are coming in. So we try to factor that into the memory usage. And I think it might even be worse than that. I'm still doing some calculations on what the memory usage actually is, and I think there's a way to optimize that, but currently it's copying the bytes directly from the local cache. Finally, we've run into a few deadlocks. So make sure you have strict timeouts on your cache getter functions. I think appropriate timeouts are always a good idea for a distributed service. But this is something that we didn't think about early on, and it's really important. You don't want a distributed system to be deadlocked. And finally, a cold cluster, because it's strictly read-through and there's no way to pre-warm explicitly, there's no way to set values, you want to make sure to roll your cluster when you're doing upgrades so that you don't have all of your nodes cold at the same instant. So depending on your workload, you might want to look at sort of an appropriate time period between upgrading your nodes. And hopefully this goes without saying, but because it's distributed, you want to make sure there's backwards compatibility between the data that you're storing. So if you add values to your protocol buffers, your code will need to handle older versions of that until the cluster is completely, until all the data has been expired. And unless you've restarted every node, there's no way to guarantee that there's no old data there. So that's it. Thank you very much. Yes?
When your peer list changes and the hash rate gets recalculated, how much of your hash gets expired? Like, is that a really impactful thing when one node goes away?
Okay, so the question was when your peer list changes and your hash ring is updated, is that very impactful, or does that add a lot of extra load, I think, to the cluster? I don't have any numbers for you. My guess would be if it's just a single node changing, it wouldn't be a huge change, especially if your most requested items are in the hot cache anyway. You're going to be able to serve those immediately locally. I would have to do some experimenting on it. I'm not exactly sure. I think if your cluster is large enough, it's not going to be much of an issue. If you just have like 1 or 2 nodes, yeah, that would be 2 or 3 nodes, that would be a big difference. Yeah.
Do you release your OpenCV bindings?
Not yet. We are definitely working on that. They're a little incomplete right now because they're solving the problems that we're working on. But yeah, that was actually a really interesting project, and I have a lot to say about using CGO. But yeah, we're working on open sourcing that. So keep an eye on COTAP's repositories.
You mentioned video in the beginning. There seems to be a single byte slice all the time. A video is kind of too big for that.
Yeah, great question. So sorry, I want to make sure I repeat the questions. So did everybody hear his question? Okay. So the question back here was, I mentioned video, and images are single byte slices. Video is much larger, and you can deal with streaming video. So if you actually look at the presentation, I'll go back to this because not everybody might have gotten it. Check out Brad's presentation here on dl.google.com. They actually cached all of the files in dl.google.com in 2 megabyte chunks. So almost like a file system stores data. They would actually cache in those chunks, and then to form a single file, they would simply request all those chunks from different nodes in the cache and sort of put that together in a single read seeker for the client. And that's similarly to how we're handling video. We basically are storing those chunks and returning those chunks to the client as it requests them. So we do, HLS is one of the formats we support, and HLS has segments, and so we're just returning those segments to the client as it requests them. I think that's a great way to handle very, very large byte segments. Yeah. Any other questions? All right. Thanks so much.